Hello and welcome. Find a comfortable place to rest. Let your shoulders drop, soften your jaw, and allow your breathing to settle into its own gentle rhythm. Tonight, we're going on a quiet journey through some of the most patient, powerful forces on our planet. We'll explore volcanoes and mountains, those ancient giants that have watched over Earth for longer than we can truly imagine. There's no need to concentrate too hard. Just let the words wash over you like a slow tide. Let's begin. Imagine, if you will, that mountains are storytellers. Not the kind that speak in words, but the kind that hold their tales in layers of stone, in the curves of their slopes, in the way light falls across their faces at dawn. Mountains are Earth's oldest storytellers, and their stories unfold across timescales that make human history look like the blink of an eye. A mountain doesn't rush. It can't. Its very existence is a lesson in patience, in the slow accumulation of moments that eventually become something magnificent. Mountains form in different ways, each method as patient as the last. Some are born from the slow collision of tectonic plates, those massive puzzle pieces that make up Earth's outer shell. When two plates push against each other, the rock between them has nowhere to go but up. Slowly, over millions of years, the land buckles and folds like fabric being pushed together on a table. These are called fold mountains, and they're some of the most dramatic ranges on Earth. The Himalayas, home to Mount Everest, formed this way. The Indian plate crashed into the Eurasian plate, and the land between them crumpled upward into the tallest peaks our planet has ever known. Other mountains form along fault lines, where the Earth's crust cracks and massive blocks of rock shift upward or downward. These are fault block mountains, and they often have one steep face and one gentler slope. The Sierra Nevada range in California formed this way through countless earthquakes over millions of years, each one lifting the rock a little higher. And then there are volcanic mountains, which we'll explore more deeply in just a moment. These are built not by the collision of plates, but by material rising from deep within the Earth, layer upon layer of cooled lava and ash. What's remarkable is that these processes are still happening. Right now, as you rest here, the Himalayas are growing taller. Not quickly, of course. They gain only about 5 millimeters each year, roughly the length of a grain of rice. But they've been doing this for 50 million years, and they'll continue long after we're gone. The plates beneath them push against each other with the same steady pressure they've applied since before dinosaurs walked the Earth. There's something deeply comforting about this, isn't there? The knowledge that some things move at their own pace, undisturbed by the frantic speed of modern life. Mountains teach us about patience embedded in stone. Every peak you've ever seen, every summit that's ever touched the clouds, took more time to form than human civilization has existed. When you look at a mountain, you're looking at millions of years of pressure, collision and uplift. You're seeing deep time made visible. And in that perspective, our own worries, our deadlines and anxieties become a little smaller, a little more manageable. Mountains remind us that some things cannot be rushed and that there's beauty in the slow unfolding of natural processes. Now let's turn our attention to volcanoes, those places where the Earth quite literally breathes fire. If mountains are the planet's storytellers, then volcanoes are its pressure valves, its way of releasing the immense heat and energy that builds up in its depths. Deep beneath your feet, dozens of miles down, the Earth is hot. Not just warm, but hot enough to melt rock. This molten rock, called magma when it's underground, forms in the Earth's mantle, the thick layer between the crust we live on and the core at the center of everything. Magma forms because the Earth is still cooling down from its formation 4.5 billion years ago. Heat rises from the core, and in certain conditions, this heat melts the rock in the mantle. The molten rock is less dense than the solid rock around it, so it begins to rise, slowly making its way toward the surface. This journey can take thousands of years. The magma doesn't rush. It moves through cracks and weaknesses in the rock above, accumulating in chambers, waiting, building pressure. When magma finally reaches the surface, we call it lava, and we have a volcanic eruption. But volcanoes don't just appear randomly. They exist in specific places for specific reasons, and those reasons tell us about the constant, restless motion of our planet's surface. Most volcanoes form along the boundaries of tectonic plates. Remember those puzzle pieces we mentioned earlier? Where they pull apart, magma can rise through the gap. Where one plate slides beneath another, water and minerals get dragged down into the hot mantle, lowering the melting point of rock and creating magma. And then there are hot spots, mysterious plumes of extra hot mantle material that burn through the crust like a blowtorch, creating volcanoes even in the middle of tectonic plates. The Ring of Fire is Earth's most famous volcanic region. It's a horseshoe-shaped zone around the Pacific Ocean where tectonic plates collide and subduct, creating a nearly continuous chain of volcanoes. 3/4 of the world's active and dormant volcanoes sit along this ring. From the Andes Mountains in South America, up through Central America, along the western coast of North America, across to Japan, and down through the Philippines and Indonesia, the Ring of Fire contains some of the most powerful volcanic systems on Earth. It sounds dramatic, and in many ways it is. But remember that most of the time, these volcanoes are quiet. They sit and wait, building pressure over decades or centuries, releasing it in moments of spectacular energy. Even in destruction, even in the violence of an eruption, there's a rhythm, a purpose. Volcanoes are part of Earth's natural cycle. They release pressure that would otherwise build to dangerous levels. They bring nutrients from deep within the planet to the surface. They create new land, new mountains, new possibilities for life. The Hawaiian Islands, for example, are entirely volcanic. They didn't exist before volcanic activity built them up from the ocean floor, layer by layer, eruption by eruption. What seems like destruction from one perspective is creation from another. Nature doesn't judge its own processes. It simply continues the slow work of transformation. Let's climb now, in our imagination, up the side of a mountain. As we ascend, something interesting happens. The air changes. With every 1,000 feet we gain in elevation, the air pressure drops. There's less atmosphere above us, pressing down. At sea level, the weight of all the air above creates about 14.7 pounds of pressure on every square inch of our body. We don't notice it because we're built for it, evolved for it. But as we climb, that pressure decreases. At the summit of Mount Everest, the air pressure is only about 1/3 of what it is at sea level. There's the same percentage of oxygen in the air, but there's less air overall, which means less oxygen in each breath. This is why high altitude affects us so profoundly. Our bodies have to work harder to get the oxygen they need. Our hearts beat faster. We breathe more rapidly. If we ascend too quickly, we can experience altitude sickness. a collection of symptoms that remind us we're not adapted to these thin atmospheric conditions. But people who live at high altitudes, who have spent generations in places like the Andes or the Himalayas, develop adaptations. Their blood carries oxygen more efficiently. Their lungs process air differently. The human body is remarkably flexible when given time to adjust. And here's something that surprises many people. Mountains are cold at their peaks, even though they're closer to the sun. You might think that getting closer to the source of heat would make things warmer, but the atmosphere doesn't work that way. The sun's energy passes through the air and warms the ground. The ground then heats the air directly above it. This means the warmest air is usually at lower elevations where it's in contact with the sun-warmed surface. As you climb higher, you move away from this heated surface, and the air grows colder. For every 1,000 feet you ascend, the temperature typically drops about 3.5 degrees Fahrenheit. This is why mountains can have snow on their peaks even in tropical regions, even when it's warm at their base. Mountains also create their own weather patterns in remarkable ways. When wind encounters a mountain, it has to rise up and over it. As the air rises, it expands because there's less pressure at higher altitudes. When air expands, it cools. If it cools enough, the moisture in it condenses into clouds and possibly precipitation. This is why mountains often have clouds clinging to their slopes, why they create rain and snow on their windward sides. The air then flows down the other side, compresses, warms, and becomes drier. This creates what we call a rain shadow, where one side of a mountain range can be lush and wet, while the other side is dry, sometimes even desert. Have you ever seen those smooth, lens-shaped clouds that hover above mountain peaks? They're called lenticular clouds, and they form when stable, moist air flows over a mountain, creating a series of waves in the atmosphere downwind of the peak. The clouds form at the crest of these waves and dissolve at the troughs, making them appear stationary, even though air is constantly flowing through them. They look almost like UFOs, these perfectly sculpted clouds, and they're a visible reminder that mountains influence the invisible ocean of air around them. There's something almost meditative about understanding these processes, isn't there? Mountains shape wind and water, temperature and cloud. They create boundaries in the atmosphere just by existing, just by standing where they stand. They teach us about layers, about transitions, about how one thing flowing into another can create something beautiful and unexpected. Now, let's consider something that seems contradictory at first. Volcanic soil is among the most fertile on Earth. You might think that volcanoes, with their destructive power, would leave behind landscapes where nothing could grow. But the opposite is true. When a volcano erupts, it brings up material from deep within the earth, material rich in minerals that plants need. Volcanic ash contains potassium, phosphorus, calcium, magnesium, and many other nutrients essential for plant growth. When this ash weathers and breaks down, it becomes incredibly rich soil. This is why, throughout history, people have lived near active volcanoes despite the danger. The soil is too valuable to abandon. Some of the world's most productive agricultural regions are in volcanic areas. The slopes of Mount Vesuvius in Italy, the volcano that destroyed Pompeii, have been farmed for thousands of years. The island of Java in Indonesia, one of the most volcanically active places on Earth, supports one of the highest population densities in the world. largely because its volcanic soil is so productive. Coffee grown in volcanic soil, particularly in places like Hawaii, Guatemala, and Indonesia, is prized for its complex flavors. Wine grapes thrive in volcanic soil in regions from Sicily to the Canary Islands. Even rice, one of humanity's most important crops, grows exceptionally well in the volcanic soils of parts of Asia. What we see here is nature's cycle of renewal and rebirth. A volcano erupts, and in the immediate aftermath, the landscape can look devastated. Ash buries everything. Lava flows destroy what they touch. But given time, life returns. Seeds blow in on the wind or are carried by birds. They find purchase in the mineral-rich ash. Plants begin to grow, and they grow vigorously in this fertile medium. Within a few years, green returns. Within decades, forests can reclaim the land. The destruction was never an ending, just a transformation, a reset that ultimately increases the land's ability to support life. This is one of the most profound lessons volcanoes teach us, that from destruction can bloom abundance, that endings and beginnings are often the same event viewed from different moments in time, that nature doesn't waste anything, not even catastrophe. There's something deeply hopeful in this understanding, something that can comfort us when we face our own moments of upheaval and change. Let's pause for a moment and consider something unusual, the sound of mountains. What does a mountain sound like? At first, you might think they're silent, these massive formations of rock and ice. But mountains are actually full of sound if you know how to listen. Wind is perhaps the most constant sound in mountain environments. Mountains create their own wind patterns, as we discussed earlier, and these winds can howl through passes, whisper across plateaus, or roar in storms. The sound of wind in mountains is different from wind anywhere else. It has a quality shaped by the terrain itself, by the way air funnels through valleys and rushes over ridges. If a mountain has glaciers, those rivers of ice make their own music. Glaciers are constantly moving, flowing downhill under their own immense weight, at speeds ranging from a few inches to a few feet per day. As they move, the ice cracks and groans. Deep within a glacier, you can hear pops and creaks as the ice adjusts to pressure. Sometimes chunks break off the front of the glacier in events called calving, and these create sounds like thunder or breaking glass. In the quiet of a mountain night, you might hear a glacier settling, adjusting, continuing its ancient flow toward lower ground. Mountains with active volcanoes have their own soundscape. Before many eruptions, the volcano begins to rumble. This isn't just the sound of magma moving, though that's part of it. It's also the sound of rock breaking, of gas pressure building, of the entire mountain adjusting to the forces working within it. These sounds travel through the ground as well as through the air. Seismometers can detect them long before human ears can, giving scientists warning that an eruption might be coming. The sound of an actual eruption can be profound. When Krakatoa erupted in 1883, the explosion was heard 3,000 miles away. It was the loudest sound in recorded history, and it ruptured the eardrums of sailors 40 miles distant. But perhaps the most striking sound in high mountains is silence. At extreme altitudes, above most of the atmosphere, sound behaves differently. There's less air to carry it, so sounds don't travel as far. In the death zone above 26,000 feet on the highest peaks, climbers report an eerie quiet. Their own breathing sounds loud in their ears, but other sounds seem muffled, distant. This silence is almost meditative for some, unsettling for others. It's a reminder that we're in a place not quite meant for us, a place at the boundary of our world and the void beyond. Learning to listen to what seems silent is perhaps one of the skills mountains teach best. Not everything that matters makes noise. Not everything important announces itself. Sometimes the most profound truths are the quietest ones, the ones we have to stop and pay attention to hear. Mountains measure time differently than we do. This is not metaphor, it's literally true. Consider that a human lifetime, even a long one, is roughly 100 years. A century. That feels substantial to us because it's all we have, the entire scope of our existence if we're fortunate. But to a mountain, 100 years is nothing. It's a single breath. It's a moment so brief as to be almost unmeasurable. The youngest mountains on Earth, the Himalayas, are 50 million years old. 50 million years. Try to wrap your mind around that span of time. You can't. Not really. None of us can. It's too vast for human comprehension. The oldest mountains are even more ancient. The Appalachian Mountains in eastern North America, worn smooth by time, are approximately 480 million years old. When they were young and sharp-peaked like the Rockies are today, the first plants were just beginning to colonize the land. Trilobites swam in ancient seas. Dinosaurs wouldn't appear for another 200 million years. And through all that time, through mass extinctions and ice ages, through the rise and fall of countless species, the Appalachians stood. They've been worn down by erosion, certainly. They were once as tall as the Himalayas. But they remain, patient and enduring. Erosion is the universe's slowest sculptor. It works with water, wind, and ice, each wearing away at rock grain by grain. Water is particularly effective. It flows into cracks in the rock. When it freezes, it expands, forcing the cracks wider. Over countless cycles of freezing and thawing, solid rock can be split apart. Rain, slightly acidic from carbon dioxide in the atmosphere, slowly dissolves certain types of rock. Rivers carry away tiny particles of mountains, transporting them to the sea. Over millions of years, this process can level the tallest peaks. Wind carries sand and dust, and these particles act like sandpaper, slowly wearing away exposed rock surfaces. In deserts and high plateaus where wind is constant and vegetation scarce, you can see the effects clearly in the smooth, sculpted surfaces of stone. Glaciers, those rivers of ice, are perhaps the most powerful erosive force of all. As they flow, they pluck rocks from the ground and carry them along. These rocks act like grinding tools, carving deep valleys and polishing the bedrock beneath. Many of the most dramatic mountain landscapes on Earth, including the valleys of Yosemite and the fjords of Norway, were carved by glaciers. What's remarkable is how these processes give mountains their character. Young mountains, recently uplifted and not yet heavily eroded, have sharp peaks and steep faces. The Himalayas, the Andes, the Rockies all show this youthful angularity. Old mountains, worn down by hundreds of millions of years of erosion, are gentler, more rounded. The Appalachians, the Scottish Highlands, the Urals, all have this softened quality. They're no less beautiful for their age, just different, shaped by time into something more serene. There's a perspective here that can be genuinely helpful in our daily lives. When we're stressed about deadlines, worried about changes, anxious about the future, it can help to remember geological time. Mountains teach us that the pace we move at, the speed our culture demands is not the only valid rhythm. Some things unfold slowly and are better for it. Some processes cannot be rushed. Some transformations require more time than a single human lifetime can provide, and that's okay. We're part of something much larger and longer than ourselves, and there's comfort in that knowledge. Now let me tell you about a world you've likely never seen, the realm of underwater volcanoes. Most people, when they think of volcanoes, picture a mountain on land, cone-shaped, perhaps with lava flowing down its sides. But the truth is that most volcanic activity on Earth happens where we can't see it, deep beneath the surface of the ocean. In fact, roughly 80% of all volcanic eruptions occur underwater. There are more volcanoes on the ocean floor than on all the continents combined. We live on a volcanic planet. We just can't see most of it. The reason for this is the structure of Earth's crust. The ocean floor is constantly being created and destroyed in a process called seafloor spreading. In the middle of most ocean basins, there's a mid-ocean ridge, a massive underwater mountain range formed by volcanic activity. At these ridges, tectonic plates are pulling apart. As they separate, magma rises from the mantle to fill the gap. When it reaches the cold ocean water, it solidifies into new oceanic crust. This process is happening right now, continuously, all around the world. The Mid-Atlantic Ridge, which runs down the center of the Atlantic Ocean, is creating about 1 inch of new seafloor every year on each side. That might not sound like much, but it adds up. Over millions of years, this process has widened the Atlantic Ocean to its current size. Underwater volcanic eruptions look different from eruptions on land. When lava emerges on the seafloor, the cold water causes it to cool almost instantly, forming distinctive shapes called pillow lava. Imagine toothpaste being squeezed out of a tube, but instead of being soft, it immediately hardens into rounded, pillow-like mounds. These pile up, one on top of another, building the volcanic mountain higher. Sometimes these underwater mountains grow tall enough to break the surface of the ocean, and when they do, they become volcanic islands. Iceland is sitting right on the Mid-Atlantic Ridge, and it's constantly being created and recreated by volcanic activity. Hawaii is built on a hotspot, a plume of extra hot mantle material that's been punching through the Pacific Plate for millions of years, creating a chain of islands as the plate moves over it. Some of the most remarkable features on Earth exist around underwater volcanoes. These are hydrothermal vents, places where seawater seeps down through cracks in the oceanic crust, gets heated to extreme temperatures by the magma below, dissolves minerals from the rock, and then shoots back up into the ocean. These vents can reach temperatures of 700 degrees Fahrenheit, but the water doesn't boil because of the intense pressure at depth. The mineral-rich water coming out of the vents precipitates when it hits the cold ocean water, forming chimney-like structures that can grow many feet tall. Some of these are white or light-colored and are called white smokers. Others are dark and are called black smokers. What's truly amazing is that these hydrothermal vents, in one of the most extreme environments on Earth, support thriving ecosystems. Before the first vent communities were discovered in the late 1970s, scientists didn't think life could exist in such conditions. The vents are in absolute darkness, far deeper than sunlight can penetrate. The water is superheated and filled with chemicals that would be toxic to most organisms. And yet, life has found a way. Bacteria at the vents use the chemicals in the hot water as an energy source instead of sunlight, a process called chemosynthesis. These bacteria form the base of a food chain that includes giant tube worms, ghostly white crabs, specialized clams, and many other species found nowhere else on Earth. These ecosystems are oases in the deep ocean desert. The surrounding seafloor is relatively barren, with sparse life eking out an existence on the rain of organic matter from above. But around a hydrothermal vent, life flourishes in abundance. The discovery of these communities changed our understanding of where and how life can exist. If life can thrive in these extreme conditions on Earth, maybe it could exist in similar environments on other worlds, perhaps around hydrothermal vents on Jupiter's moon Europa or Saturn's moon Enceladus, both of which have subsurface oceans. This is one of the hidden processes supporting visible worlds. Most islands, most of the continents themselves, rest on foundations built by volcanic activity. The fertile soil we depend on for food is renewed by volcanic eruptions. The carbon cycle, which regulates Earth's climate over geological time, depends on volcanoes releasing carbon dioxide and rock weathering removing it. We live on the surface, in the visible world, but that surface is supported and sustained by processes happening deep below, most of which we never see or think about. Volcanoes remind us that the foundation matters, that what's hidden is often what makes everything else possible. Let's explore how mountains shape human culture in ways both obvious and subtle. Throughout history, in nearly every culture that's existed near mountains, those mountains have taken on sacred significance. There's something about peaks reaching toward the sky that speaks to the human imagination. Mountains feel closer to the divine, perhaps because they're closer to the heavens, or perhaps because they're so massive and enduring compared to human life. In ancient Greek mythology, Mount Olympus was home to the gods. In Judeo-Christian tradition, Moses received the 10 Commandments on Mount Sinai. In Hinduism and Buddhism, Mount Kailash in Tibet is sacred, believed to be the abode of gods and the center of the world. Shinto in Japan reveres many mountains, particularly Mount Fuji. Indigenous peoples across the Americas, from the Andes to the Rockies to the Appalachians, have their own sacred peaks and mountain stories. The pattern repeats across continents and cultures. Mountains are special, worthy of reverence, places where the earthly and the divine meet. Why is this? Part of it is surely practical. Mountains are dramatic, impressive, inspiring. They dominate the landscape. They can't be ignored. They influence weather, create boundaries, serve as landmarks. But there's something psychological happening too. Studies have shown that experiences in nature, particularly in dramatic natural settings like mountains, can induce feelings of awe, and awe has measurable effects on human psychology. It makes us feel smaller in a good way, connected to something larger than ourselves. It reduces stress, increases feelings of well-being, and can even make people behave more generously toward others. Mountains don't just inspire religious feeling. They generate genuine psychological and emotional responses that transcend culture. Mountains also create cultural boundaries in literal ways. Before modern transportation, mountain ranges were serious obstacles. They separated populations, allowing distinct cultures, languages, and traditions to develop on either side. The Alps separated the Mediterranean world from northern Europe. The Himalayas created a barrier between India and Tibet. The Andes isolated different groups of indigenous peoples. These weren't absolute barriers, of course. People crossed mountains, traded over them, migrated through passes. But they were significant enough to slow the mixing of populations and allow diversity to flourish. Interestingly, mountains also create cultural identities. Mountain peoples often share certain characteristics regardless of which mountains they live in. They tend to be hardy, adapted to difficult conditions. They often have distinct traditions, clothing, architecture, and foods suited to high-altitude environments. Swiss, Tibetan, Andean, and Nepalese cultures are all very different, but they share the common experience of living with mountains, and that experience shapes them in recognizable ways. For many people around the world, mountains are places of pilgrimage. The Camino de Santiago in Spain, while not entirely mountainous, crosses several ranges. In Japan, climbing Mount Fuji is a spiritual practice for many. The trek to Mount Kailash involves circling the mountain, a practice undertaken by Hindus, Buddhists, and Jains. Pilgrimage routes to high places exist on every continent, and they serve similar purposes: to challenge the body, to remove oneself from everyday concerns, to seek clarity or spiritual insight at altitude, in thin air, in places that feel removed from the normal world. There's also a purely human drive to climb mountains, to reach summits, to stand on top and look down at the world below. When George Mallory was asked why he wanted to climb Mount Everest, he famously replied, "Because it's there." This might seem flippant, but it captures something true about human nature. We see a challenge and we want to meet it. We see a height and we want to reach it. Mountains call to something in us. Some need to test ourselves, to see from new perspectives, to stand where few have stood. The view from a mountain summit is unlike any other. You can see the curve of the earth on a clear day from high enough peaks. You're literally looking down on clouds. The world spreads out below you in a way that makes its geography clear. You can see how valleys connect, how rivers flow, how land is shaped. There's a sense of accomplishment, certainly, but also a sense of perspective. From a summit, your everyday concerns seem very far away. The problems that loomed large at lower elevations shrink. You're reminded of your place in a vast landscape, in a world that existed long before you and will continue long after. This is why mountains are places of retreat and reflection. Monasteries are often built on mountains or in high valleys. Writers, artists, and thinkers have long sought out mountain cabins and retreats when they need to work without distraction or find inspiration. There's something about altitude, about being surrounded by peaks and sky, that clarifies thought. Maybe it's the thin air, or maybe it's the removal from ordinary life, or maybe it's the awe that mountains inspire. Whatever the mechanism, mountains have served as places for inner work across cultures and centuries. Our connection to vertical landscapes does seem to mirror inner journeys, doesn't it? We speak of high and low moods, of peaks of happiness and valleys of despair. We talk about climbing toward goals, about uphill struggles and downhill slides. The metaphors are so ingrained in our language that we barely notice them, but they reveal something about how we understand our internal lives. Mountains give us a physical manifestation of abstract concepts like difficulty, achievement, perspective, and transcendence. They let us act out inner journeys in the outer world. When we climb a mountain, we're not just moving our bodies through space. We're also doing something symbolic, something that resonates with our psychological and spiritual lives. Now let's delve deeper into the types of volcanic eruptions, because not all eruptions are created equal. The character of a volcanic eruption depends largely on the type of magma involved and the amount of gas dissolved within it. Some eruptions are gentle, almost peaceful. Others are catastrophically violent. Understanding why gives us insight into the temperament of these geological giants. Magma comes in different varieties, classified mainly by their silica content. Silica is silicon dioxide, the same compound that makes up quartz and sand. Low silica magma, called basaltic or mafic magma, is relatively fluid. It flows easily, like honey on a warm day. When this type of magma erupts, it tends to create relatively gentle eruptions. The lava flows out and spreads across the landscape in rivers of molten rock. The Hawaiian volcanoes typically erupt this way. You can sometimes stand fairly close to an active lava flow, watching the glowing orange rock creep across the ground, hearing it hiss and crackle as it cools. It's dangerous, certainly, but it's a slow-moving danger, one you can usually walk away from. High silica magma, called rhyolitic or felsic magma, is much thicker, more viscous. It flows like cold peanut butter. This thickness causes problems. Gas dissolved in the magma has a hard time escaping. As the magma rises toward the surface and pressure decreases, the gas wants to come out of solution, like bubbles forming when you open a bottle of soda. But if the magma is too thick, the gas can't escape easily. Pressure builds. Eventually, the pressure becomes too great and the eruption is explosive. The magma is blown apart into tiny fragments of volcanic ash and rock. These explosive eruptions are the ones that make headlines, that can affect global climate, that can bury cities. The eruption of Mount Vesuvius in 79 AD, which buried Pompeii and Herculaneum, was this type of explosive eruption. The eruption column rose miles into the sky and then collapsed, sending pyroclastic flows racing down the mountain slopes. A pyroclastic flow is a mixture of hot gas and volcanic particles that can travel at speeds over 100 miles per hour and reach temperatures of 1,000 degrees Fahrenheit. Nothing in its path survives. The people of Pompeii were killed almost instantly, and their bodies were buried in ash so quickly that the ash preserved the shapes of their final moments. Centuries later, archaeologists filled these cavities with plaster, creating haunting casts of people caught in the midst of ordinary life when catastrophe struck. But volcanic eruptions don't just affect the immediate area. Large explosive eruptions can influence global climate. When a volcano ejects massive amounts of ash and sulfur dioxide into the stratosphere, these particles can spread around the globe, reflecting sunlight back into space and cooling the Earth's surface. The eruption of Mount Tambora in Indonesia in 1815 was so massive that the following year, 1816, became known as the Year Without a Summer. Snow fell in June in New England. Crops failed across Europe. The disruption contributed to food shortages and social unrest, all because of one volcano on an island most Europeans had never heard of. More recently, the eruption of Mount Pinatubo in the Philippines in 1991 cooled global temperatures by about 1 degree Fahrenheit for several years. It was a reminder that we live on a dynamic planet, one that can change its own climate through natural processes that were happening long before humans appeared and will continue long after we're gone. Volcanic gases are another fascinating aspect of eruptions. When magma rises, it releases gases that were dissolved in it at high pressure. Water vapor is the most abundant volcanic gas, making up 60 to 90% of gas emissions. Carbon dioxide is also common, as is sulfur dioxide, which can form sulfuric acid in the atmosphere. Hydrogen sulfide, hydrogen, carbon monoxide, and various other gases can also be present. These gases can be detected by instruments, and changes in gas emissions often signal that magma is moving beneath a volcano, potentially leading to an eruption. Some volcanoes release gas continuously, even when they're not erupting. These steady emissions can create localized hazards, but they also provide a safety valve, allowing pressure to escape gradually rather than building to explosive levels. Scientists monitor volcanic gas emissions carefully because they provide a window into what's happening deep underground in the magma chambers and conduits that feed the volcano. Let's talk about the different types of volcanoes themselves, because their shapes tell stories about how they form and how they erupt. Shield volcanoes are broad and gently sloped, looking somewhat like a warrior's shield lying on the ground. These form from low silica lava that flows easily. Each eruption adds a thin layer of lava, and over time, over thousands of eruptions, the volcano grows wide and tall, but never steep. The Hawaiian Islands are shield volcanoes, and Mauna Loa on the Big Island is the world's largest active volcano by volume. From its base on the ocean floor to its summit, it's taller than Mount Everest, though most of it is underwater. Stratovolcanoes, also called composite volcanoes, are the classic cone-shaped mountains most people picture when they think of a volcano. Mount Fuji, Mount Rainier, Mount St. Helens. These are all stratovolcanoes. They form from a mix of lava flows and explosive eruptions that deposit ash and rock fragments. The alternating layers of lava and ash build up over time into steep, symmetrical cones. These volcanoes tend to erupt more explosively than shield volcanoes because their magma is typically higher in silica. Cinder cone volcanoes are the smallest type, built from fragments of lava thrown into the air during eruptions. These fragments, called cinders or scoria, fall around the vent, building up a circular or oval cone. Most cinder cones are only active for a short time, geologically speaking, perhaps a few years or decades, and then they go dormant. They're like geological mayflies, brief and small compared to their larger volcanic cousins. Calderas are a special type of volcanic feature. When a volcano erupts so explosively that it empties its magma chamber, the ground above can collapse into the void, creating a large depression. Some calderas are miles across. Crater Lake in Oregon sits in a caldera formed when Mount Mazama erupted catastrophically about 7,700 years ago. Yellowstone National Park sits atop one of the world's largest calderas, the remnant of a super eruption that occurred about 640,000 years ago. The Yellowstone caldera is roughly 45 miles across. When people call Yellowstone a supervolcano, this is what they mean: a volcanic system so large that its eruptions can have global consequences. Supervolcanoes are a special category defined not by their size, but by the magnitude of their eruptions. A supervolcanic eruption ejects more than 240 cubic miles of material. For perspective, the eruption of Mount St. Helens in 1980 ejected about a quarter of a cubic mile. Supervolcanoes are thousands of times larger. There have been several dozen supervolcanic eruptions in Earth's history. The most recent was the Taupo eruption in New Zealand, about 26,500 years ago. The most famous might be the Toba eruption in Indonesia about 74,000 years ago, which may have caused a volcanic winter that lasted years and significantly affected human populations. Should we worry about supervolcanoes? Well, yes and no. They're rare. The intervals between super eruptions are measured in hundreds of thousands of years. The Yellowstone system, for example, has erupted in super eruption mode 3 times in the past 2.1 million years. That's roughly one every 700,000 years. The last one was 640,000 years ago, which means we might be getting close to the next one on geological timescales. But geological timescales are long. The next super eruption could be tomorrow, or it could be 300,000 years from now. Scientists monitor these systems carefully, but there's no indication that an eruption is imminent at Yellowstone or any other known supervolcano. What's perhaps more important than worrying is appreciating. These volcanic systems, even the dangerous ones, are part of what makes Earth a living planet. They recycle materials from deep in the mantle back to the surface. They create new land. They contribute to the atmosphere and oceans. Without volcanic activity, Earth would be a very different place, likely one less hospitable to life as we know it. Let's shift our focus to the glaciers that cap many of the world's mountains, because these rivers of ice are sculptors of landscapes and records of climate history. Glaciers form in places where more snow falls in winter than melts in summer. Year after year, the snow accumulates. The weight of new snow compresses the older snow beneath it, gradually transforming it into ice. When the ice becomes thick enough, typically around 100 to 150 feet, it begins to flow under its own weight, and you have a glacier. Mountain glaciers, also called alpine glaciers, flow down valleys like slow rivers. They move because ice, despite being solid, can deform plastically under pressure. The ice at the bottom of the glacier under the most pressure flows like a very thick fluid. The ice at the top is more brittle and can crack, forming crevasses, those deep fissures that make glacier travel dangerous. The speed of glacier movement varies widely. Some glaciers move only inches per year. Others can move several feet per day. A few unusual glaciers, called surging glaciers, periodically speed up dramatically, moving hundreds of feet in a day for short periods. As glaciers move, they reshape the landscape with immense power. They pluck rocks from the valley floor and walls, a process called quarrying. These rocks become embedded in the ice and act like the teeth of a giant file, grinding and scraping the bedrock beneath. The rock flour produced by this grinding gives glacial meltwater its distinctive milky appearance. Over thousands of years, a glacier can carve a V-shaped river valley into a U-shaped glacial valley with steep walls and a flat floor. The valleys of Yosemite, including the famous Yosemite Valley itself, were shaped by glaciers during the ice ages. Glaciers also create other distinctive landforms. Cirques are bowl-shaped depressions carved into mountainsides at the head of a glacier. Aretes are sharp ridges formed when glaciers carve away rock from both sides. A horn is a peak with 3 or more cirques carved into it from different sides. The Matterhorn in the Alps is the classic example. Fjords are valleys carved by glaciers that later flooded with seawater. The coast of Norway is famous for its fjords, some of which are thousands of feet deep. But glaciers are more than landscape sculptors. They're also archives of climate history. As snow accumulates and compresses into ice, it traps tiny bubbles of air. These bubbles are samples of the ancient atmosphere, preserved for thousands or even hundreds of thousands of years. By drilling ice cores from glaciers and ice sheets, scientists can analyze these air bubbles and reconstruct past atmospheric conditions. We know about carbon dioxide levels in the atmosphere going back nearly 1 million years because of ice cores drilled in Antarctica. We can see in the ice the record of volcanic eruptions, dust storms, and even human activities like the Industrial Revolution. Sadly, many mountain glaciers around the world are retreating, melting faster than they're accumulating new ice. This is one of the clearest signals of our changing climate. Glaciers that have existed for thousands of years are disappearing within human lifetimes. The ice that took millennia to form is melting in decades. This isn't just an aesthetic loss, though it is that. Many communities depend on glacial meltwater for drinking water and agriculture. As glaciers shrink, the summer meltwater they provide decreases, potentially causing water shortages for millions of people. Yet even in this sobering reality, there's something to appreciate about glaciers. They remind us that ice is a force, that frozen water is anything but static, that the solid parts of our planet flow and change just like the liquid and gaseous parts. They connect us to ice ages past and perhaps ice ages future. They show us that Earth's climate has always changed, though rarely as rapidly as it's changing now. And they demonstrate once again that we live on a dynamic planet, always in motion, always transforming. Let's consider the phenomenon of geothermal energy, that heat from Earth's interior that powers volcanoes but can also be harnessed by humans. In volcanic regions, water can seep down through cracks in the rock, get heated by magma or hot rock below, and then rise back to the surface. Sometimes it emerges as hot springs, pools of water heated from below to temperatures that can be pleasantly warm or scalding hot. People have bathed in hot springs for thousands of years, appreciating their warmth and sometimes attributing healing properties to them. Other times, the heated water bursts from the ground under pressure as a geyser. Geysers are rare. There are only about 1,000 active geysers in the world, and they require specific conditions: a reliable water source, an intense heat source, a plumbing system of cracks and chambers in the rock, and a constriction in the plumbing that allows pressure to build. When conditions are right, water at depth heats beyond the boiling point, but stays liquid because of the pressure above it. Eventually, some steam forces its way up, reducing the pressure, which allows more water to flash to steam, and the whole system erupts in a fountain of hot water and steam. Old Faithful in Yellowstone is probably the world's most famous geyser, erupting roughly every 90 minutes with impressive regularity. Humans have learned to tap this geothermal energy for practical purposes. In Iceland, a country sitting on the mid-Atlantic ridge with abundant volcanic heat, geothermal energy heats about 90% of homes. Wells drilled into hot rock bring up steam or hot water that can drive turbines to generate electricity or be used directly for heating. Geothermal power plants operate in many volcanic regions around the world, from the Philippines to Italy to New Zealand to the western United States. It's a form of renewable energy, constantly replenished by the heat from Earth's interior, a heat that will last for billions of years. There's something poetic about using the same volcanic heat that can destroy to instead power our lives and warm our homes. It's another example of how what seems purely destructive can, with understanding and care, become generative. The fire beneath our feet doesn't have to be only a threat. It can also be a resource, a gift from the deep earth. Volcanic landscapes also host some of Earth's most unusual ecosystems. We already discussed hydrothermal vents in the deep ocean, but volcanic areas on land have their own specialized life. Some organisms thrive in hot springs that would boil most life forms. Thermophilic bacteria, organisms that love heat, live in water above 120 degrees Fahrenheit. Some can survive in water near boiling. These organisms were among the earliest forms of life on Earth, and studying them gives us clues about how life might have originated in hot, chemical-rich environments. Plants colonize volcanic landscapes with remarkable speed once conditions allow. Some species are specialists, adapted to grow in volcanic soils, to tolerate high levels of certain minerals, to thrive where other plants struggle. In Hawaii, you can see the succession of plant life across lava flows of different ages. The youngest flows, just years old, are bare black rock. Slightly older flows have lichens and mosses, the pioneers that can grow on bare rock. Older still, and you find ferns, grasses, shrubs. Give it a century or two, and forests return. The native ohia tree is often among the first woody plants to colonize new lava flows in Hawaii, sometimes growing directly from cracks in the rock. Animals follow the plants. Insects arrive, then birds, then larger animals. In time, volcanic landscapes become as full of life as any other, sometimes more so because of the rich soils. This process of succession, of life reclaiming what seemed barren and lifeless, plays out across volcanic regions worldwide. It's a testament to life's resilience, its ability to adapt, to wait, to slowly transform even the harshest environments into homes. Mountains, too, host specialized ecosystems adapted to altitude. As you climb a mountain, you pass through different life zones, almost like traveling from the equator toward the poles. The base of a tropical mountain might host rainforest. Climb higher and you enter cloud forest, perpetually shrouded in mist. Higher still, the forest gives way to alpine meadows, then to bare rock and ice. Each zone has its own characteristic plants and animals, adapted to the temperature, moisture and light conditions at that elevation. Alpine plants, those that grow above the tree line, are marvels of adaptation. They're typically low-growing to avoid strong winds. Many form cushions or mats, shapes that conserve heat and moisture. Their flowers are often disproportionately large and brightly colored to attract the few pollinators that venture to high altitudes. Some alpine plants can photosynthesize at temperatures barely above freezing. They've evolved antifreeze compounds in their cells to prevent ice crystals from forming and damaging their tissues. Animals in alpine zones face similar challenges. They need to cope with cold, thin air, intense UV radiation, and limited food. Mountain goats and sheep have thick insulating coats. Pikas, small relatives of rabbits that live in rocky areas above the tree line, gather plants during the brief summer and dry them like hay, storing this food for winter. High-altitude birds have more efficient lungs and hemoglobin that carries oxygen better. The bar-headed goose migrates over the Himalayas, flying at altitudes above 25,000 feet, where the air is too thin for most birds to fly. These adaptations remind us that life is endlessly creative in finding solutions to challenges. Where there seems to be no way to survive, life finds a way. Mountains, like volcanic landscapes, might seem inhospitable, but they're actually rich with life. Just life that's adapted to conditions very different from the lowlands most of us inhabit. Let's talk about something that connects mountains, volcanoes, and the very foundations of our planet: plate tectonics. This theory, developed mainly in the 1960s, revolutionized geology by explaining how the Earth's surface moves and changes. The lithosphere, the rigid outer layer of the planet, is broken into about a dozen major plates and several smaller ones. These plates float on the hotter, more pliable asthenosphere beneath them. Heat from the Earth's interior creates convection currents in the mantle, and these currents drag the plates along, moving them at rates of a few centimeters per year. Where plates collide, one of several things can happen. If both plates carry continents, the collision crumples both, forming mountain ranges like the Himalayas. If one plate is oceanic crust and the other is continental crust, the denser oceanic plate usually slides beneath the continental plate in a process called subduction. This creates a deep ocean trench where they meet and often produces a chain of volcanoes on the overriding plate. The Andes Mountains form this way as the oceanic Nazca Plate subducts beneath the South American plate. Where plates pull apart, magma rises to fill the gap, creating new crust. This happens at mid-ocean ridges, as we discussed, but it can also happen on continents. The East African Rift is a place where a continent is being torn apart. Volcanic activity is common there, and millions of years from now, the rift may widen enough to become a new ocean, splitting Africa into two landmasses. Where plates slide past each other horizontally, you get transform boundaries. The San Andreas Fault in California is probably the most famous example. These boundaries don't typically produce volcanoes, but they do produce earthquakes as the plates grind past each other. Sometimes smoothly, but often in sudden lurches, as friction locks them together until stress overcomes resistance. Understanding plate tectonics helps us understand why mountains and volcanoes are where they are. They're not random. They mark the boundaries and the forces that shape our planet's surface. And recognizing this, we can see the Earth not as a static ball of rock, but as a dynamic system, with its surface constantly moving, constantly being recycled and renewed. The ocean floor is young geologically, nowhere older than about 200 million years, because it's constantly being created at mid-ocean ridges and destroyed at subduction zones. The continents are older, with some rocks over 4 billion years old, because continental crust is less dense and doesn't subduct easily. This recycling is essential for maintaining Earth's habitability. The carbon cycle depends on it. Carbon dioxide from the atmosphere is absorbed by the oceans and incorporated into sediments. These sediments are subducted, and the carbon is eventually released back into the atmosphere through volcanic eruptions. Without this cycle, without plate tectonics and volcanoes, Earth's climate would have drifted to extremes long ago, probably becoming too hot or too cold for life as we know it. Venus, our sister planet, may be an example of what happens when plate tectonics stops. Its surface is hellishly hot, with a runaway greenhouse effect, possibly because it lacks the plate tectonics to recycle carbon dioxide. So when we appreciate mountains and volcanoes, we're also appreciating the planetary processes that make Earth a living world, capable of supporting the incredible diversity of life we see around us. We're appreciating a system that's billions of years old and will continue for billions more. A system that renews itself, that balances itself, that makes our existence possible. As we come toward the end of our journey tonight, let's take a moment to appreciate the patient, powerful nature of these formations we've explored. Mountains and volcanoes are the product of forces and timescales that dwarf human experience. They're built by the slow movement of tectonic plates, by the accumulation of lava flows and ash, by the buckling and folding of the Earth's crust under immense pressure. They're worn down by erosion, grain by grain over millions of years. They influence weather, create habitats, provide resources, shape cultures, and inspire awe. And they continue their work whether we notice or not. Right now, as you rest here listening to these words, the processes that build and reshape mountains are ongoing. The Indian plate pushes into the Eurasian plate, lifting the Himalayas a few millimeters higher. Magma rises through the crust beneath Yellowstone, adding to the pressure in that massive volcanic system. Rain falls on the Appalachians, carrying away dissolved minerals to the sea. Glaciers in the Alps and the Andes flow imperceptibly downhill, carving the valleys a tiny bit deeper. Volcanic activity on the seafloor creates new crust, widening ocean basins. The work continues, as it has for billions of years, as it will for billions more. There's something deeply comforting about this continuity. In a world that often feels chaotic and uncertain, where change happens rapidly and the future seems unpredictable, geological processes continue at their own pace, unrushed and unchanging in their fundamental nature. The same forces that built ancient mountains are building new ones. The same processes that created the earliest volcanic islands continue to create them today. Nature doesn't reinvent these mechanisms. It uses them again and again, patient and consistent. While you rest tonight, while you let sleep come in its own time, know that mountains stand under starlight exactly as they've stood for millennia. Volcanoes breathe through vents and cracks, releasing pressure in small ways so it doesn't build catastrophically. The Earth's plates continue their slow dance, moving at about the speed your fingernails grow, but moving nonetheless. Ice forms in cracks and expands, splitting rock. Wind carries away grains of sand. Water dissolves minerals and carries them to the sea. The work of geological time continues, whether we witness it or not. Can you carry this geological patience into sleep with you? Can you imagine your breathing slowing to the pace of mountains, your heartbeat settling into the rhythm of the deep earth? Your thoughts are like clouds passing over peaks, here and then gone, leaving the mountain unchanged. Your worries are like rain, falling on stone, running off, making their way eventually to the sea. The mountains remain, the deep processes continue, and you, resting here, are part of it all, made of the same atoms that make up mountains and magma, star stuff and stone, all connected in the vast, slow dance of matter and energy that we call the universe. Let your body sink into rest. Let your mind drift like mist in a mountain valley. There's nowhere you need to be, nothing you need to do. The mountains will stand their watch. The volcanoes will tend their fires. The earth will continue its patient work. And you can rest, knowing you're held by a planet that's been doing this for 4.5 billion years and knows exactly what it's doing. Think of the timescales we've explored tonight. 50 million years for the Himalayas, 480 million years for The Appalachians, billions of years for the Earth itself. In this vastness, your individual worries, your deadlines and anxieties become vanishingly small. Not unimportant to you, certainly, but small in the grand scheme, manageable, temporary. Mountains teach us this perspective. They've witnessed countless generations of every species that's lived on Earth. They've seen climates change, seas rise and fall, ice sheets advance and retreat. Through it all, they've stood, patient witnesses to the pageant of life. And yet, they're not eternal. They rise and fall on geological timescales. The mountains we see today will eventually erode away. New mountains will rise from the sea or from colliding continents. The Earth's surface is always changing, always renewing itself. Nothing is truly permanent except change itself. But that change happens so slowly, so gradually, that from our perspective, it might as well be permanence. The mountains will outlast us, outlast our civilizations, outlast perhaps even our species. There's a comfort in that, a reminder that we're part of something much larger than ourselves. Sleep well. The mountains will still be there in the morning, waiting under the dawn light, exactly as they've waited through countless mornings before, exactly as they'll wait through countless mornings to come. The volcanoes will still tend their fires in the deep places of the Earth, building and rebuilding the planet's surface according to rhythms older than life itself. And the glaciers, those rivers of ice, will continue their slow flow, sculpting valleys, preserving records of climate, demonstrating that even solid ice can flow given time and weight. Rest now. Let the patience of stone and the slow breath of the earth carry you into sleep. Let the knowledge that you exist on a planet of such grandeur, such ancient processes, such patient power, comfort you. You are held by mountains billions of years in the making. You breathe an atmosphere created and maintained by geological processes. You are, quite literally, made of star stuff, cooked in the hearts of ancient suns, scattered into space, gathered by gravity into planets, transformed by geological forces into the elements that make up your body. Breathe in, breathe out. The ancient rhythms continue. Mountains rise grain by grain. Volcanoes build islands in the sea. Glaciers carve valleys. Plates drift across the Earth's surface. And you can rest, knowing you're part of this vast, slow dance, this patient unfolding of matter and energy and time. The mountains remember everything and nothing. They hold the record of their formation in their rocks, in the layers that can be read like pages in a book. But they don't remember the way we do. They simply exist, shaped by the past, continuing into the future, patient and enduring. May you find some of that patience tonight. May you rest as deeply and completely as stone rests in the heart of a mountain. May your sleep be as undisturbed as a summit above the clouds, quiet and still, and far from the concerns of the lowlands. And when you wake, may you carry some of that mountain peace with you, some of that volcanic patience, some of that glacial acceptance of time's passage. The world moves at its own pace, the deep world of geology and climate and the slow dance of continents. We can rush, or we can move at a more measured speed, remembering that some things cannot be hurried, that some processes unfold in their own time, and that there's wisdom in accepting this. Good night. Rest well. The mountains are standing their watch. The earth continues its work, and you can sleep, held and safe, part of something ancient and enduring and vast beyond measure. Let go of the day. Let go of your worries. Let yourself sink into the deep rest that comes from knowing you're held by forces as old as the planet itself, as patient as stone, as enduring as the slow dance of continents across the face of the earth. Sleep now. The mountains will still be there when you wake, and so will you, refreshed and renewed, ready to face whatever the day brings, carrying with you perhaps a little of the mountain's patience, a little of the volcano's deep fire, a little of the glacier's slow certainty. Rest well. The ancient earth stands watch, and you can sleep. Breathe, rest, sleep. The patient earth continues its work, and you are part of it, now and always, held in the slow rhythms of geological time, safe in the knowledge that these processes have continued for billions of years and will continue for billions more. Rest now. Rest deeply. Rest completely. The mountains remember. The earth endures. And you can sleep.